this session, we will talk about Rayleigh Ritz method. We both are your VR tutor, which are going to aid you in understanding this concept of Rayleigh Ritz method. Now, we will start with the case study. Now, there's a cantilever beam. Now, cantilever beam is a type of a beam where force is acting perpendicular to the neutral axis and it is fixed from one end. Now you can see here there's a swimming pool and a healthy boy want to jump from that pool. However, if you see, the pool cannot withstand the force given by the boy or the weight of the boy, so it is going a very large deflection. So we're going to, in today's session, we're going to find out the deflection using Rayleigh Ritz method. So what basically is Rayleigh Ritz method? Rayleigh Ritz method is an approximate method to calculate deflection, as we have seen in a cantilever beam, when an externally applied load is happening. For example, in the previous case of swimming pool, the boy was the load, externally applied load, which was walking when he was trying to jump in the swimming pool. Now, Rayleigh Ritz method relies on principle of minimum potential energy, which states that total energy of the system is conserved. The whole Rayleigh Ritz method starts with assumption of displacement function. Sometimes we call it deflection function, as well as trial function or shape function. Now, steps to find Rayleigh Ritz method. First step is you need to assume a trial function. Sometimes it's called displacement function, sometimes it is called deflection function, sometimes it is called shape function. These are two examples of trial function, because we will call it trial function throughout the session. Let the trial function be y is equal to a1 a2x plus a3x square when it is in the form of polynomial. Other case is when the Rayleigh Ritz method, when the deflection function is in the form of trigonometric function. Now when you are choosing y is equal to a1 plus a2x plus a3x square, in that case the problem is very easier to solve. However, the deflection, the answer obtained, is not close to the actual result, so approximation varies. However, in the second case, y is equal to a1 plus sine x, it's a trigonometric function, so our results are accurate. However, it is bit time consuming. So in the numerical, the trial function either will be given or you need to find it out. Now, second step, after we have chosen the trial function, the next step is to calculate the minimum potential energy principle. Now you can see in the figure, a man is trying to compress the spring, so he is doing work against the system. Whenever the work is done against the system, it is always negative. That's why if we consider the total energy of the system, strain energy, for example, the inside strain energy of the spring, it's always positive. It won't allow any external force to compress it. That's why it's positive. However, when an external force is acting, it is always negative. That's why work done against the system is zero. Now, minimum potential energy states that if we differentiate the total energy of the system with respect to dx, it will become zero. That is minimum potential energy. That is how we find out Rayleigh Ritz method. Now we'll try to solve a numerical. Now there's a cantilever beam, as you have seen. This is the case. A boy is trying to jump from the swimming pool, jump into the swimming pool with the beam, the help of beam. However, the beam cannot withstand the deflection. So we need to calculate, or we need to formulate a deflection using Rayleigh Ritz method. Now first step, as discussed earlier, we need to select a trial function. So we had selected y is equal to a1 plus a2x plus a3x square, deflection, where y is equal to the deflection and deflection is unknown. Second step is we need to consider the total potential energy of the system, which is equal to U minus W. As explained earlier, minus is the external work acting in the system and energy remains constant. Now d pi by dx, it states that the rule of minimum potential energy, it need to be differentiated. Now this we need to understand. If you remember the earlier formula of beam, the total strain energy of the system is given by EI by 2. If we integrate from 0 to L, L is the total length of the beam. You can see here there is a cow who is dancing on the cantilever beam. Here L is the total length of the beam, and the strain energy of the system is given by this formula, the boundary condition. Now if you see the cow at the end where the cow is dancing, the deflection is too high. Got it? However, at the fixed end there is no deflection and the slope is also 0. So both deflection as well as slope is 0 at the fixed end. So this will be the boundary condition of the system. Now first we will take only 3 value approximate because there are 2 unknown x and y. If we start increasing, our complexity will increase. It will take more time to solve the problem. Now we will set the boundary condition. Now as we know, slope as well as deflection at the fixed end of the cantilever beam is 0. So we will apply the boundary condition. Now you can see here dy by dx, the first derivative of the deflection function, is equal to 0, as this is a cantilever beam. So the slope is 0. Now we will equate it to 0. So we got the relation between A2 and A3, and A1 is equal to 0. The reason is, if we put at x equal to 0, if we put the value of x equal to 0 and y is equal to 0, A1 is completely 0. And the value of A2 we are getting from dy by dx, so equal to 0. Now you can interchange the value A2 to A3. Our intention is to keep whole system in either A2 or A3 form. So finally this is our equation. Boom, we got the equation. So we finally got, by our assumption and hit and trial method, our deflection equation. Now deflection equation is equal to minus A3x square. Now Rayleigh Ritz method. Now if you see the cow, when the cow is coming at the end at x equal to 0, at x equal to L, the deflection is maximum. Again I will repeat, when the cow, we will see it again, when the cow is coming at the end and trying to jump at the end, the deflection is maximum. That means the work done on the system by external force at the end is 0. That means if we write work done is equal to force into y max, y is equal to minus A3x square, which we got from the previous slide. So work done on the system is force into minus A3L square. The total potential energy of the system is equal to U minus W. U is the strain energy of the system and W is the external work done on the system. Now U, if we recall, the strain energy of the beam is given by half EI integrate 0 to L, where L is the total length of the system. Y is the trial function which we have assumed, and I will repeat the process to differentiate it. First derivative of y, A2 plus 2A3x, then second derivative is equal to 2A3, and we will try to put the value in the system of our strain energy. So we're going to get this value. So U is equal to half into 4EIAL3 square. It's as simple. We just need to square it and put out the constant. Now if you integrate dx, we will get the value L. So finally we will be getting 2EAI AL square in the system. So the strain energy of the system is 2EI AL square. And work done, maximum work done we got from earlier value. So total strain energy of the system is U minus W. And we will put the value which we obtained from the previous slide. Now we will differentiate it with respect to A3 because A3 is unknown to us. And our whole system is varying with the value of A3. So when we differentiate with respect to A3, we are getting this value. So boom, so A3 is equal to minus FL 4EI. It doesn't matter you take A3 or A2. So your variable is only one. So we got A3 here. Now we will put the value of A3 in the equation. So y is equal to minus A3x square. So we got the relation of both A2 and A3. Now if we substitute the value, we got our final deflection, FLX square by 4EI. This is the deflection of the slope. Now the maximum deflection which we obtained is F3 FL cube by 4EI. However, the actual value is FL cube by 3EI. So we can see by Rayleigh Ritz method, the approximate value deviate from the actual value. So there is an error. Now, hope you understand this slide. Like and subscribe.